Lesson 4-2, graphing polynomial functions. So we have done some graphing of polynomial functions here. We're going to do more in this lesson and then analyze some of the key features with them. First part is looking at the location principle. So if the value of a polynomial function, f of x, which this is also referring to your y, changes signs from one value of x to the next, then there is a zero between those two x-intercepts. This is called the location principle. So if you're looking at a table, and let's say this was -1, 0, and 1, and then we had -2, 1, and then this went to 5, there is a sign change in our y's here. That means there is a 0 or an x-intercept in between these x's, -1 and 0. That's all they mean by the location principle. So we're going to take a look at our first example. It says determine the consecutive integer values of x between which each real 0 of f of x equaling x to the fourth minus 2x cubed minus x squared plus 1 is located. Then we're going to draw the graph. And the graph is just going to be a rough estimate of the graph based on our points that we're going to choose. So I'm going to first enter this into my calculator. So we have x to the fourth minus 2x cubed minus x squared plus 1. Now if I go to second graph, see my table of values, I'm going to go to -2 to 4. Okay, so -2 is 29, -1 is 3, 0 is 1, 1 is -1, 2 is -3, 3 is 19, and 4 is 113. So I want to focus in on my y's. So I have a change here, change of signs there, and I have a change of signs here. That means between 0 and 1, there's an x-intercept, or a 0. So it crosses the axis between 0 and 1. And it also crosses between 2 and 3 because I see another sign change there. So between the consecutive integers, so I'm going to say between 0 and 1, and between 2 and 3. I'm going to graph these. These are going to come by 1. So I'm just going to graph the ones that I can fit on here. So I have -1, 3. So -1, 3 would be here. 0, 1. 1, -1. 2, -3. And then 3, 19 would be way up here. So now if I were to draw my graph here, it looks something like this. There'll be some other curves in here, but that's just a general estimate of that. And if I were to go back to my calculator and let's just graph this one. So you can see it, I just don't have this little bend in here. So I could actually go down here, come across, then bend, then it comes back up. But that's just a general estimate of what our graph will look like. Next, determine the consecutive integer values of x between each real 0 of f of x equaling 2x to the fourth minus x cubed minus 2x squared minus 2 is located, and then draw the graph. So again, we're going to take our calculator, we're going to type in our equation. So we got 2x to the fourth minus x cubed minus 3x squared, and then I think it's minus 2. Go to second graph, see a table of features. So it's have -2, 26, -1, -2, 0, -2, 1, -4, 2, 10, 3, 106, and 4, 398. Now, if I look at that, see if there's any sign changes. I do have a sign change here, and I have a sign change here. So we would say between -2 and -1, and between 1 and 2. For these, we'll just count by ones again. So -226. -226 would be way up here. Then we have -1, -2. This would be down here, 0, -2. And we have 1 and -4. We have 2, 10. That'd be roughly here. And if we did 3, 106, that'd be way up here off the screen. So now we can draw our graph. Now that it comes down here, crosses between -2 and -1, comes here. We know that it has to come back up at some point. So we're just going to come back up here. Then it's going to come back down at some point here. And then it goes up here. So it looks something similar to that. So now if I take my calculator and let's compare what they have, our calculator, to with our drawing. So something similar what we have here. Just want to make sure you do go down here because it's not the same there. So don't draw a straight line here. Make sure it goes below a little bit and then comes back up. Next part is extrema of a polynomial. Extrema occur at relative maxima or minima of the function. Point A is a relative minimum. So point A is a relative minimum. It is a low point, but just not the lowest point. And point B is a relative maximum because it is a high point, just not the highest, because you can see the arrow is going up here. Both A and B are extrema. The graph of a polynomial of a degree n has at most n minus 1 extrema. So whatever the degree is, so if it was x squared, it has at most 2 minus 1, 1 extrema. Which, if it's an x squared, that's a polynomial, which just means it opens upward or opens downward. I have a maximum of 1 extrema, so I can either have a minimum or a maximum here. Example 2, identify the extrema here. So we're going to use a table to graph this function and then estimate the x-coordinates at which the relative maxima and relative minima occur. So again, to make this a little bit quicker, we'll put this into our calculator. So we have x cubed plus, this is 1x squared minus 5x minus 2. If we do second graph, get a table of values, let's go up to -4. We have -30. We have -5. We got 4. We got 3. We got -2, -5. We got 0. And if we go down one more, we got 19. We need to estimate the x-coordinates. So at which the relative maximum and minimum occur. So if we plot these on our graph, I'm not going to plot all of them. I'm just going to do a few of them. So -3, -5. So I have -3, -5 here. -2, 4. I have a point here. I would have -1, 3. Here we have 0, -2. And we have 1, -5. And we have 2, 0. So based on what I have here, I can now draw my graph. So it looks something like here. So it looks something like that. So if I have 3, a degree of 3, if I subtract 1, I should have 2. That means I should have a maximum of two extremas, which I do have 2 extremas here. So the x would be roughly, so the x coordinates would be roughly 2 or negative 2, and we would say a positive 1. Now, if we want to use our calculator to just verify that, if we go to graph, here's a maximum, so a negative 2, so roughly negative 2, here roughly a positive 1 there. And to find that more specifically, if I did second trace, I want to find a maximum, so I could do number 4. Left bound would be here, enter, go to the minimum, or the right side, enter a third time. X is negative 1.6 rounded to, that would be about negative 2. And then we can do the same thing for the x coordinate there. Moving on to our next example. Let's use the table of values of this function to estimate the x coordinates at which the relative maxima and relative minima occur. So again, let's put it on our calculator to come up with our table. So we have negative x to the 4th minus x cubed plus 5x squared plus x minus 3. I go second graph, fill this table in. So we got negative 15, we got 7, we got 1, negative 3, 1, negative 5, and negative 63. Now if I graph that, actually we can figure that out from here. So the minima, see there's a sign change here, there's a sign change here, sign change here. Then it keeps going. So the lowest point looks like at negative 5. So the x would be 2. And let's see, we have, so if we did 4 minus 1, we can have a maximum of 3 extremas. So crosses there, crosses here. We could have one at negative 3. And we could also have one at negative 15, but let's verify that with our graph. So if I graph this, so for this one, if I did, this one looks about be about negative 2, but let's just check this one a second. I was actually looking at the wrong numbers here. So here, this would be at negative 3. This one would be at 0. And this one would be at 2. So negative 3, 0. And this is about 2. But let's just check this first one. Let's do the minimum. So that's a low point there. That one's roughly 1.2. So we'll say that's about 2. But let's double check this. If I did, that one was a maximum. So if I did a 4, left side, enter, right side, enter a third time. So 1.3, that would be We have about 2, so that's fine. And then the other side, if we were to go all the way up here, so a negative 1.9. We had originally a negative 3, but let's check this. Second trace. This is a maximum, number 4. Go to the left bound, enter, go to the right bound, enter, hit enter a third time, and we have negative 1.9, so about a negative 2, which would make sense because I was thinking of the other direction. So you're coming up from negative 15 to 7, and then you're coming back down. So that would be negative 2, 0. And here we would have a low point relative. We had another high point, so at 1. So here, so that would be about 1 for the maximum. And the minimum would be 0 because we have a low point, so the x coordinate would be there. So yeah, that would be the case there. So if you're unsure from the table, just use the graph, and the graph would be a little more accurate than maybe is easier from the table. Moving on to example 3, analyze a polynomial function. The total number of certified pilots in the United States is approximated by f of x equaling 0.0000903 x to the fourth minus 0.0166 x to the third plus 0.762 x squared plus 6.317 x plus 7.708, where x is the number of years after 1930 and f of x is the number of pilots in thousands. Graph the function and describe its key features over the relevant domain. And you can already see that the relative domain is going to be greater than or equal to 0. So now if we take our calculator and we're just going to type in that equation, clear this. So we have 0 points. We got 1, 2, 3, 4 zeros. 1, 2, 3, 4, 903 x to the fourth minus 0.0166 x cubed. Then we have plus 0.762 be x squared plus 6.317 x plus 7.708. And if I hit graph, okay, and then go to second graph, we're going to do the table of values here. So we have 0 and 7.708. Let's count by, let me change this windows. We're going to count these by tens. Now let's see our table. There we go. Then we have 131.38, 320. I'll just run, 320.5, 507.96, 648.36, 50 was 717.93, 714.62, 70 was 658. Then we had 589.36. Then we had 90 was 571.62. And if we hit our graph, there again you can see our graph. Now on a coordinate plane, we're only going to use the relevant ones, so we would have to be more on the more on the right-hand side of 0. So if we change the Windows settings to minimum, let's do 0. X maximum, let's go to 90. We'll count by tens. Minimum would be 0 all the way to, let's do 800. Count by 100s. Actually, let's count by 50s. That might make it a little bit easier. Now if we hit graph, there's the relevant parts that we would be looking at. Then we can describe. Here we're going to describe the key features over the relevant domain. Now here is our graph, which is very similar to what we had here. So we made that table, we put our numbers in there, we used our calculator to graph that. Now we're going to do the key features. So the domain and range, based on here, the domain would be x such that x has to be greater than or equal to 0. And the range, y such that y, if we look at our table, which the lowest number was 7.708, so y is greater than or equal to 7.708. The extrema, so the extremas that we have, so the maximum, the high point was between, so 50 years and 60 years since 1930. So that would be between 1980 and 1990. We have a max, or a relative max, between 1980 and 1990. And then a minimum, so relative minimum, looks like between 80 years after and 90 years after. So 80 years after would be 2010. And 90 years after would be 2020. Next part, other key features, the end behavior. For this one, since we're not going to go to the left, it's always going to go to the right. The arrow is pointing upwards, so as x approaches positive infinity, y approaches positive infinity. The intercepts, we know it crosses the y-axis at 0 and 7.708. And the x-intercept, there is none. Symmetry, there is none. We on to our next example. Number of quarters produced by the U.S. Mint can be approximated by the function f of x equaling negative f of x equaling 16.4x cubed minus 149.5x squared minus 148.9x plus 3215.4, where x is the number of years since 2005 and f of x is the total number of quarters produced in millions. Use a graph of the function to complete the table and describe its key features. So here we're going to complete that table here. So we'll grab our calculator. The y equals, clear everything. So we got 16.4 x cubed minus 149.5 x squared minus 148.9 x plus 3215.4. Second graph, we're going to change that table feature here. We're going to count by twos. and we're going to start at 0. There we go, and then we have 3215.4, 2450.8, 1277.4, 482.4, 853, and 3176.4. So there's our table. Then we can use that table now to graph. Actually, we can use that table now to do the key features. So the relevant domain has to be greater than or equal to 0. The relative range is going to be f of x is greater than or equal to the lowest point, it looks like 853. Actually, no, there is one lower. There's 482.4. So about 482. I'm just going to keep it at 482 instead of the decimals. There's a relative minimum between which two parts. So the low point. So it goes from 32 to 24 to 12 to 4 to 8. So we would have a relative minimum between which years. So this is the years since 2005. So if we have a low point at 482, so that's 6 years. So that's 2011. Between 2011 and 8 years after would be the next one, which would be 2013. And then the y-intercept, where is across the y-axis? That's when x is 0. That would be roughly 3,215. The graph of the function does not have symmetry. And the graph, it is unreasonable to assume that the trend will continue indefinitely. If you look at the trend, if we look at the graph here, so if we graph this, then we continue going up more and more. Example 4, use a polynomial function and technology to model. As the table shows, U.S. backpack sales in millions of dollars according to the Travel Goods Association. Make a scatter plot and a curve of best fit to show the trend line over time. Then determine the backpacks since 2015. So to do this, we're going to break this into steps. So the first step is to enter the data into our calculator. We'll grab our calculator here, and it says let the year 2000 be represented by 0, and enter the years since 2000 in list 1, and the backpack sales in list 2. So I'm going to come over here. I'm going to go to, first I'm going to clear what I have in here. Then I'm going to go to second, actually not second, let's go to stat, edit. And in list 1, 2000 is year 0, so 0, and then 1, 2, 3, all the way up to 14. Says to year 14, or 2014. And then over here in list 2, we're going to put the backpack sales, so 1140, 1144, 1113, 1134, 1164, 1180, 1364, 1436, 1246, 1235, 14, 19, 17, 73, 19, 30, 22, 55, 27, 79. Now we have all those in here. We go to the next part. The next part is graph the scatter plot. To do that, we need to change the stat plot of our calculator. So let's go to our calculator. We need to go to second, y equals. We need to turn plot one on. So I'm going to hit enter, turn this on, and we need this first one highlighted, which I do have. And just make sure X list is 1 and list Y list is 2, just showing that that's what we are having, where our data is located. Now if I hit zoom number 9, which is zoom stat, you can see my graph there. Let me go back to my Windows. Okay, that's fine. Now to our next part, we're going to determine the polynomial function of best fits. So determine the model that best fits the data, perform linear, quadratic, and cubic, quartic regressions, and compare the coefficient determination of R squared. The one that's closest to 1 is the one that we want to use. The regression equation for the coefficient rounded to the nearest tenth. So here I'm going to get out of here. I'm going to hit second, actually not second, I'm going to hit stat. We're going to go to calculate, and we're going to check each of these. If I go to linear regression, number 4, hit enter. You notice I don't see the R squared here, so that means I got to turn my diagnostic on. To do that, I hit second, 0 for catalog. Go all the way down till you see diagnostic on, and then hit enter, and when you see done, then go to stat, calculate, number 4, enter. And here we have 0.68. I'm just going to put over here linear was 0.68. So that's not very close to 1. So we know it's not going to be linear. Go back to stats, calculate. Now let's do quadratic, number 5. Hit enter, and we have 0.91. Quadratic, we had 0.91345. We do that one. That one's close. That's 91. 0.91. Let's go to stats, calculate. Let's try cubic. Number 6. There we have 0.9644. So cubic was 0.9644. Or I could do 45. So that's very close. So right now it looks like it's going to be cubic, but we have to check quartic. So a stat calculates to quartic, number 7, enter, and we have 0.97. So it looks like it's quartic. So if the quartic, we will look at our A, and it tells us our equations. So we need to the nearest tenth. So this would be 0.2 x to the 4th minus 3.9 x cubed plus 26.4 x squared minus 43.6 x. And let's move this over just 10 more. Go down plus 1,140. Actually, 39.9. And that would be our regression line for that. Step 4 is to graph and evaluate the regression function. So if we're going to put that in our calculator to graph all of that, now if I go to y equals, I'm going to hit vars, go down to number 5, statistics, go over to EQ, and choose number 1. It puts my equation in here. Then if I hit graph, it now puts the line in here. So that's the line of best fit. So if you look at, compare the two, they look very similar. Now what I want to do is to determine the total sales in 2015, find the value of the function for x equaling 15. So if I go to second trace, I want to find the value, number 1, and I'm going to choose 15, and then hit enter. It's going to give me 3,523.2514, which is the same as what they have in that picture there. So in 2015, there was about, we could say, $3,523 billion. 3,523, so this is in billions. So I'm going to put a decimal point. So it'd be $3.523 billion in backpack sales. Our last question here, it says to estimate the amount of lumber that can be harvested from a tree, foresters measured the diameter of each tree, determine the polynomial function of best fit, where x represents the diameter of a tree in inches, and y is the estimated volume measured in board feet. Then estimate the volume of a tree with a diameter of 35 inches. So we are going to enter these into our calculator. So I'm going to go to Stat, Edit, just going to clear everything. Now, since this one's not dealing with years, I put the table in exactly the way it is. So I have 17, 19, 20, 23, 25, 28, 32, 38, 39, and 41. The other column, we have 19, 25, 32, 57, 71, 113, 123, 252, 259, 294. Now if I want to calculate, so a stats calculate, I don't think it's going to be linear because it's not increasing at this constant rate. So let's see if it's quadratic. So if I hit quadratic, I would have 0.9903. So quadratic was 0.99032. So that's very close to 1. Let's do stat calculates. Let's try cubic. 6.99094. Cubic was 0.99095. That one's bigger. Right now it looks like it's cubic. Let's try another one. Stats calculates. Let's go to number 7, quartic. And this one is 0.991. So this is quartic. Since this one's a quartic, let's write the equation. So we have y equals, and we're going to, let's just do it to the nearest tenth. So it's be y equals negative 6.5 x to the fourth plus 0.1 x cubed minus 3.5x squared plus 69.1x minus 491.4. Then we're going to use that to estimate the volume of a 35-inch diameter tree to the nearest board foot. So to do this, I'm going to go to my y equals and clear this, hit vars, number 5 statistics, go to EQ, number 1, and then I'm going to graph this. Let me hit zoom number 9. There we go. If you don't see the points right away, just hit zoom stat number 9. There we go, and then we go to second, trace the value. So number 1, and this would be 35, diameter is 35, hit enter. That would give us 187.69. Now here we have 187.69. Now if you look at that, that would be almost the exact amount, but they want us to estimate this. So based on the equation that we have, and looking at my equation, there was one part that I missed when I was writing our equations. So if I went back to here, you'll notice that this a has e to the negative 4th. That means I have to move the decimal place 4 places to the left. If I move it 4 places to the left, 1, 2, 3, 4, I would have 0 here, 0 here, decimal point would be there. So my answer, this would be roughly 0.000 negative 0.0006 x to the 4th. Now, if we were to put 35 in for x here, you would get x equaling roughly 108. But if we use our calculator, we would have, if we put it exactly on the calculator, you'd have about 187. But either way, that would be acceptable if you use this formula, or if you use the exact formula on your calculator, then you would get 187. That is our lesson on graphing polynomial functions.